The atmosphere is always moving. The Earth's rotation combines with the immense energy coming from the Sun to cause atmospheric circulation. Most weather occurs in the troposphere, which experiences the greatest differences in temperature. Near the equator, the Sun's energy falls perpendicular to the surface, so any given area receives the maximum possible solar heating. The same amount of solar energy falls on polar regions, but that energy is spread over a much greater surface area, so the surface is heated less. This is one reason the poles are so much colder than the tropics. Another is the tilt of the Earth's axis, which causes the seasons. The difference in temperature between the tropics and the poles drives our largest atmospheric circulation patterns. This red line shows how the same amount of sunlight spreads over a much larger surface area near the poles, leaving polar regions much colder than equatorial areas. As temperatures on the surface of the Earth rise and fall, the atmosphere attempts to gain equilibrium, and warm air circulates toward cooler areas. This heat transfer from warmer to cooler areas is called convection. The convection process results from differences in temperature and creates atmospheric circulation. The convection process begins when the warm air from the equatorial regions rises and moves toward the cooler air in the polar regions. Next, as the air cools in the polar regions, it moves toward the warmer equatorial regions. The circulation process continues as the surface of the Earth heats and cools. If the Earth didn't rotate, a huge convective circulation pattern would develop as air flowed from the poles to the equator and back again. The Earth's rotation breaks this hemispheric pattern into 3 cells. The first is the Hadley cell, named after George Hadley, the 18th century scientist who first proposed the model of general circulation. Air in the Hadley cell rises at the equator and flows toward the poles, but the rotation of the Earth causes that air to reach only about 30 degrees latitude before it begins to sink. The second cell is the polar cell, named after the north and south polar regions. Air in the polar cell rises at about 60 degrees latitude and flows toward the poles where it cools and sinks. The third cell is the Ferrel cell, named after William Ferrel, another researcher of general circulation. Air in the Ferrel cell moves in a direction opposite the air in the Hadley and polar cells. Scientists believe that the movement in the Ferrel cell, which is located between 30 degrees and 60 degrees latitude, is the result of the air movement in the Hadley and polar cells. This exchange of air in the Hadley and polar cells and the reversed rotational movement of the Ferrel cell presents some possibilities for why the mid-latitudes experience a wide range of weather. You know that the difference in temperature on different areas of the Earth's surface disturbs atmospheric equilibrium and causes atmospheric circulation. But how does this process occur? You're already familiar with the concept of convection, which describes how warm air circulates toward cooler areas. Convective currents can occur anywhere the Earth's surface is heated unevenly. You probably remember that the heating action of the sun, which also occurs unequally over the Earth's surface, results in warmer and cooler regions of air. As cool air warms, it loses density, just as warm air gains density as it cools. In short, unequal heating modifies air density. As warm air rises, cooler, denser air replaces it, upsetting the atmospheric equilibrium, and thus this unequal heating creates circulation patterns. But what causes the cool, dense air to replace the warm, rising air? As solar heating causes warm, less dense air to rise, the air molecules expand, creating areas of low pressure. However, the cool, dense air is packed tightly together, which creates areas of high pressure. To reestablish atmospheric equilibrium, the cool, dense air in high-pressure areas flows to the warm, less dense air of low-pressure areas. All of this theory about atmospheric pressure is well and good, but how does it affect your aircraft? Because the sun heats the surface of the Earth unevenly over land, sea, and different terrain elevations, air density and pressure are always changing. These variations affect your flight instruments. Most markedly, these changes affect your altimeter, which senses changes in atmospheric or barometric pressure. Because the unequal heating is the primary cause of variations in altimeter settings between weather reporting points, you must periodically update your altimeter setting to compensate for these changes. The unequal heating of the Earth's surface causes variations in air density and pressure at all altitudes, so you must adjust the altimeter for local pressure changes to produce reliable information. For example, if you're flying from a high-pressure area into a low-pressure area, an unadjusted altimeter interprets the decreasing pressure as a climb. In this situation, if you maintain the constant indicated altitude, the aircraft is actually descending slowly. Due to the pressure change, the indicated altitude displayed on an unadjusted altimeter is higher than the actual altitude. This type of altimeter error could be dangerous, especially if you're flying over obstacles or areas of rising terrain. Be sure that you obtain current pressure reports and adjust your altimeter settings during flight. The barometric pressure readings issued by weather reporting stations around the globe are converted to sea level pressure to ensure all reports are based on the same standard. Weather maps provide graphical images of weather and enable meteorologists to predict weather patterns anywhere in the world. To design these weather maps, meteorologists plot areas of varying pressure. They connect points of equal pressure with lines called isobars. The resulting isobaric models resemble the contours you've probably seen on topographic charts. In addition to After you learn the purpose of isobars, you can use them to identify. Weather maps provide graphical images of weather and enable meteorologists to predict weather patterns anywhere in the world. To design these weather maps, meteorologists plot areas of varying pressure. They connect points of equal pressure with lines called isobars. The resulting isobaric models resemble the contours you've probably seen on topographic charts. Isobars denote a measurement of atmospheric pressure in millibars. By using these isobars to connect areas of equal pressure, meteorologists can identify areas of high and low pressure. The resulting pattern of the isobars on the weather chart illustrates the pressure gradient pattern, which is the change in pressure over distance. The closer the isobars are to each other, the stronger the pressure gradient. The further apart the isobars are from each other, the weaker the pressure gradient. When the isobars form concentric shapes, they identify pressure systems, and a millibar value is placed near the center of the innermost circle. Although weather charts indicate quite a bit more information about weather systems, isobars enable you to identify the type of weather in the area you'll be flying in. After you learn the purpose of isobars, you can use them to identify different types of pressure systems on a weather map. Meteorologists have created 5 pressure system classifications. Highs are centers of high pressure surrounded on all sides by lower pressure. These areas are identified by the letter H. Lows are centers of low pressure surrounded on all sides by higher pressure. Low pressure centers are identified by the letter L. A ridge is an elongated area of relatively high pressure. A trough is an elongated area of relatively low pressure. A col designates a neutral area between 2 highs or 2 lows, or the point at which a ridge and a trough intersect. By becoming familiar with these 5 pressure systems, you can use weather chart information to identify areas in which atmospheric pressure might influence weather. In addition to using the isobars in weather charts to identify areas of atmospheric pressure, you can use them to identify wind strength. Remember that air flows from high pressure to low pressure areas. The cool, dense air causes movement in the atmosphere as it flows from high pressure areas and replaces the warm, low density air in low pressure areas. The strength of the atmospheric circulation, or wind, depends on the strength of the pressure gradient, which is a change in pressure over a distance. By applying your understanding of isobaric patterns, you can easily identify areas of strong winds. You know that the closer the isobars are to each other, the stronger the pressure gradient. Strong pressure gradients produce strong winds. Therefore, closely spaced isobars indicate areas of strong winds. You know that the more widely spaced the isobars, the weaker the pressure gradient. Weak pressure gradients produce light winds, so widely spaced isobars indicate areas of light winds. The force that causes the air to move from areas of high pressure to areas of low pressure is called the pressure gradient force. This pattern of air circulation is correct in theory, but the pressure gradient force would cause all wind to blow from high pressure areas into low pressure areas if other forces didn't also act on wind movement. These other forces deflect wind movement and help develop different circulation patterns. Weather is never simple. If the pressure gradient force were the only force that affected the movement of air, wind would always blow directly from the higher pressure area to the lower pressure area. But air movement is also affected by a phenomenon called Coriolis force, a force that results from the rotation of the Earth. Without the Coriolis force, objects such as air masses, ocean currents, and airplane flight paths would all follow a straight line. But the Coriolis force causes them to follow a curved path. This force influences the paths of all objects that move freely across the face of the Earth. In the northern hemisphere, the Coriolis force deflects moving objects to the right. The amount of deflection differs depending on the latitude. No deflection occurs at the equator, and the amount of deflection increases closer to the poles. The Earth moves at a constant rate of 1 rotation every 24 hours. The magnitude of the deflection caused by Coriolis force differs with the speed of the object. The faster the speed of the moving object, the greater the deviation. This force significantly affects bodies that move over great distances, such as air masses or aircraft. For example, Coriolis force has a major influence on air circulation. As air circulates from the equator toward the poles, Coriolis force deflects it, and it cools and falls. This action breaks atmospheric circulation into the 3-cell circulation model. The combined effects of the Coriolis force and the pressure gradient force influence the formation and movement of wind. The Coriolis force continues to deflect wind until the Coriolis force and the pressure gradient are in balance. The Coriolis force and the pressure gradient force both cause atmospheric motion or wind. Because the pressure gradient force causes air to move from high pressure areas to low pressure areas, wind in the northern hemisphere flows clockwise around high pressure areas and counterclockwise around low pressure areas. However, within about 2,000 feet above the ground, friction force from the Earth's surface slows the moving air. This force reduces the Coriolis force, and causes the wind to shift directions when near the Earth's surface, from its path along the isobars toward the lower pressure. You already know how pressure gradient force, Coriolis force, and frictional force work together to create wind, and you're familiar with the Hadley, Ferrel, and polar cells and how they cause the air in the atmosphere to circulate. Together, these elements create three distinctive global wind patterns. In the northern hemisphere, the circulation pattern of the Hadley cell causes rising tropical air to flow from the equator northward toward the pole. At approximately 30 degrees north latitude, the air has cooled sufficiently to create a high-pressure area. At this point, the air begins to flow back toward the low pressure at the equator. As the cooling air sinks toward the low-pressure area at the equator, Coriolis force deflects it to the right. These air movements create the trade winds. In the northern hemisphere, these winds are called the northeast trade winds after the steady winds that ships encountered blowing from that direction during voyages from Europe to the New World. Between 30 degrees and 60 degrees, Coriolis force and the circulation pattern of the Ferrel cell cause the prevailing westerlies. In the northern hemisphere, these winds are responsible for many of the weather movements across the United States and Canada. Between 60 degrees and the North Pole, Coriolis force and the circulation pattern of the polar cell cause the polar easterlies. Although global wind patterns affect flight in general, localized wind patterns are especially important to you as a pilot. Localized wind patterns are caused by terrain variations such as mountains, valleys, and bodies of water, and they have a significant effect on regional weather. In the southern hemisphere, the wind patterns and the Coriolis force mirror the behavior of the patterns in the northern hemisphere. If you've ever been to the ocean, you've probably enjoyed the cool winds that flow onto the beach. These winds are called sea breezes, although they can also occur at lakes or other large bodies of water. The speed of a sea breeze depends on the land-water temperature difference, and some can reach speeds of 20 knots. A well-developed sea breeze exists between 1,500 and 3,000 feet AGL. These breezes blow during the day when the sun warms the surface of the earth. The air above the water is cooler than the air above the land. A sea breeze is caused by convective circulation, which occurs during the daylight hours. The cool, dense air over the water creates an area of high pressure. The sun warms the air over the landmass, which creates an area of low pressure. The cool air over the water moves inland from the area of high pressure toward the area of low pressure. As it crosses the landmass, the cool air warms and rises, continuing the convective circle. The rising air cools and sinks as it flows back out over the water on its return flow. As the air becomes denser, it again moves toward the area of low pressure. At night, the same landmass that warmed during the day to develop the sea breeze cools quickly, reversing the temperature difference between land and water. The resulting wind is called a land breeze. The speed of a land breeze is dependent on the land-water temperature difference. Because temperature contrasts are smaller at night, land breezes are generally weaker than sea breezes. Land breezes can reach an altitude of 2,000 feet AGL and extend as far as 100 nautical miles inland. Land breezes occur at night when the land surface is cooler than the water, because the air above the water remains warmer in comparison to the air above land. Like the sea breeze pattern, convective circulation causes the land breeze pattern. The cool, dense air over the land creates an area of high pressure. The temperature of the air over the water creates an area of low pressure. The cool air over the land moves from the area of high pressure toward the area of low pressure. As it crosses the water, the air warms and rises, continuing the convective cycle. The rising air cools and sinks as it flows across the cooler landmass on its return flow. The cool, dense air flows from the high-pressure area onshore to the low-pressure area offshore. Wind patterns also develop inland, well away from bodies of water. One type, the valley breeze, flows upslope from lower regions. Valley breezes can reach speeds of 20 knots, depending on the temperature difference between the top and bottom of the slope. The greatest winds usually develop a few hundred feet AGL. These breezes blow during the day when the sun warms the air above the mountain slope. The air in the valley remains cool in comparison to the warmer upslope air. As it does with sea and land breezes, convective circulation causes the valley breeze. As the sun warms mountain slopes during the day, the adjacent air warms and rises, creating an area of low pressure. The air in the valley remains cooler, and as the upslope air rises, the air lower in the valley becomes denser by comparison, creating an area of high pressure. The low-pressure area draws the cooler, denser air in the valley upslope from the area of high pressure. The rising air cools and sinks, but return flow from the mountaintops is very weak. This return flow is called the anti-valley wind. As the air becomes denser, it once again moves toward the area of low pressure. Mountain breezes occur at night when the air at the top of the mountains is cooler than air in the valleys below. As with the speed of the valley breeze, the speed of the mountain breeze depends on the temperature difference between the top and bottom of the slope. Just before sunrise, the speed of mountain breezes along the mountain slopes and valley floors can reach 15 knots, although speeds at the base of the mountain can reach 25 knots. As it does with other breezes, convective circulation causes the valley breeze. As the higher terrain cools, the air also cools and creates an area of high pressure. The air over the valley floor remains warm, creating an area of low pressure. The air in the high-pressure area flows toward the low pressure, and the winds are directed downslope along the mountain slopes and valley floor. The warm air from the valley floor rises, creating a return flow above the mountaintops. This return flow is called the anti-mountain wind. Although any type of downslope wind can affect mountain flight, you want to be especially wary of Catabatic winds, which are typically much stronger than mountain breezes. Some Catabatic winds can be particularly severe, especially if the wind is confined to a narrow canyon. Wind speeds in canyons can typically range between 20 and 50 knots, but gust speeds can exceed 100 knots. Like all other types of breezes, Catabatic winds are caused by convective circulation. There are two types of Catabatic winds: cold downslope winds and warm downslope winds. A cold downslope wind occurs when large amounts of ice and snow accumulate in mountainous terrain and cool the overlying air to very low temperatures. The overlying air becomes extremely cold, and a shallow dome of high pressure forms. This pressure gradient force pushes the cold air through the gaps in the mountains. Although the air might warm during its descent, it is still colder than the air it displaces. A cold downslope wind can become intense as it rushes downhill from snow-covered plateaus or steep mountain slopes. The other type of Catabatic wind is the warm downslope wind. This warm downslope wind occurs when a warm air mass moves at a high altitude across a mountain range. This movement creates a trough of low pressure on the downwind side of the slope. The air flows downslope toward the low pressure below. As the air descends, the air temperature increases due to compression. The warming wind can gain more than 20 degrees in an hour and dramatically raise the temperature at the base of the mountain. Cold Catabatic winds include the Bora in Croatia, the Mistral in the Rhone Valley of France, and the Columbia River Gorge wind in the northwestern United States. Warm Catabatic winds include the Chinook, which occurs along the eastern slopes of the Rocky Mountains, the Föhn in the Alps, and the Santa Ana winds in Southern California. In this lesson, you explore the following topics: the atmosphere, atmospheric circulation, atmospheric pressure, and wind patterns.